All right, let's jump right in. We all kind of think of the internet as this magical, invisible cloud, right? But it's actually a masterpiece of physical engineering. Today, we're going to pull back that curtain and see how it was really put together by digging into a couple of crucial documents from the early 2000s that basically laid the groundwork for the digital world we all live in. So, you ever wonder what actually holds the internet together? I mean, it's more than just a bunch of servers and some cables under the ocean, right? Well, the answer, as you're about to see, is this really brilliant and surprisingly complex mix of agreed upon rules and some incredibly smart hardware. Okay, so let's set the scene. We're going back to the early 2000s. The dot-com boom is in full swing, and the demand for data is just exploding. The world was getting connected like never before, but the physical infrastructure, it was really starting to creak under the strain. And the main problem they were up against was pretty fascinating. Businesses needed these huge, super dependable data connections, to link up their offices. But the fiber optic networks that were already in the ground, well, they were literally running out of space. This was a real crisis, and they even had a name for it, fiber exhaust. And you couldn't just go out and lay more cable. That was slow, it was messy, and just unbelievably expensive. So here's the key takeaway, right? They couldn't just build a bigger network. That wasn't the answer. They had to build a smarter one. They needed to figure out a way to use the fiber they already had, but way more efficiently, more intelligently. And that challenge, it set the stage for a total revolution in how networks were built. So how in the world do you build a smarter network? Well, turns out, before you can build a single thing, you have to write the rule book. You need a common language that every single telecom company, every hardware maker can agree on and understand. This is our first layer. And the organization that stepped up to write that rulebook was the Metro Ethernet Forum, or MEF for short. Now, these guys weren't out there laying cables. No, their job was way more fundamental. They were creating the standards, the core concepts that would define this whole new generation of network services. And right at the heart of their big plan was this deceptively simple idea, the Ethernet Virtual Connection, or EVC. Now, I know the technical definition sounds a little dry, but the concept behind it is absolutely revolutionary. It's basically a way to create a private, dedicated data connection between two or more spots using nothing but software and configuration. Let me put it this way. Think of the regular internet as a massive public highway system with tons of traffic. Well, an EVC is like getting your own private, secure highway that goes directly from your office in one city to your office in another, completely bypassing all that public traffic. It's a virtual tunnel built on top of shared physical cables, but it's defined entirely by a set of rules, not by a specific wire. And this is where the MEF's genius really shines. They created this beautifully simple framework. See, they defined a service type, like a simple point-to-point connection. Then they gave it a bunch of attributes, things like speed or how reliable it is. And finally, each of those attributes had specific parameters you could set. This basically turned a super complex network service into something you could order like a pizza, with the exact toppings you wanted. Okay, so we've got the rule book, we have the plan. But rules are just ideas on paper, right? To make them real, you need a machine. So let's move to our second layer and check out the actual hardware that brought all these standardized services to life. And that machine was the Lucent Wavestar system. This quote from its 2003 planning guide pretty much says it all. It was designed to be the powerful, cost-effective hardware that could deliver these brand new, high-speed services over the fiber network that was already there. Let's just pause on that number for a second. 10 gigabits per second. Back in the early 2000s, that was just an astronomical amount of bandwidth. I mean, this was world-class, bleeding-edge performance that could finally solve that whole fiber exhaust problem. But here's the kicker. As crazy fast as it was, speed wasn't even the Wavestar's most brilliant feature. The real magic, the thing that would come to define what we all expect from the internet today, was its incredible reliability. They did it with this incredible thing called a self-healing ring. So data actually flows in both directions around a loop of fiber. Now, if a cable gets cut, let's say a construction crew accidentally digs it up, the system instantly detects it. Then, in just a few milliseconds, faster than you can even blink, it reroutes all the traffic the other way around the loop. And for the person using it, the crucial point is nothing happens. Service is never interrupted. It was like the internet suddenly grew its own immune system. Okay, so we've got the rules and we've got the hardware. But to make them work together perfectly, we need to peel back one last layer and look at the absolutely mind-bending complexity and control that was happening under the hood. Whoa, okay, don't worry, there's not going to be a quiz on this. What's important here isn't the formula itself, but what it represents. This is one of many super dense formulas from the MEF document for calculating something called frame delay variation, which today we just call jitter. The whole point was to guarantee performance with mathematical precision, making sure your video calls wouldn't stutter and your data would always arrive smoothly. And this just gives you a tiny taste. This table shows a tiny fraction of the settings an engineer could tweak. There were literally hundreds of these dials and knobs for every single connection, controlling everything from security to how data packets were bundled together. It was immensely complex, but all of it was designed to deliver one thing: a simple, reliable service. So you might be thinking, okay, these are some dusty old technical manuals. Why should I care about them today? Well, it's because the ideas we've just walked through, they're the direct ancestors of the internet that you are using right now to watch this. Let's connect the dots. So, why does all this matter? Well, first off, that whole MEF idea of standardized, sellable services, that is exactly how businesses buy high-speed internet and connect to the cloud today. Second, that powerful, self-healing optical hardware became the model for the ultra-reliable backbone of the entire internet. And maybe most importantly, the incredible uptime these systems delivered created the expectation we all have now, that the internet should just always be on, which enables everything from video streaming to online gaming to working from home. So when you boil it all down, the blueprint for our modern digital world was surprisingly simple in concept. Step 1, create a common language so everyone and everything can talk to each other. Step 2, build incredibly powerful and reliable hardware to run it all on. And with those two pieces in place, you forge the very foundation of the world we live in today. And that brings us to a final thought. The engineering we've just explored is completely invisible to us. Yet we rely on it every single second of every single day. It kind of makes you wonder, doesn't it? What other invisible infrastructure are you relying on right this very moment?